Recall that we had 3 replicates for the chemical example. This is what allowed us to estimate the variance. Majority of the time, because of resource constraints, we only have one replicate to work with only one observation. At each corner, we are taking some risks. What would happen if an unusual observation occurred? How accurate are your estimates of the effects going to be? Can you even estimate the variance? With only one observation for each TC, the sample variances from each TC can't be calculated. The reason for this is that you can't calculate a variance with one point. So, now what? Let's motivate this with an example. This is a pilot plant study with K equals 4 factors. The experimenter wanted to study the effects of these factors on the filtration rate of a resin. The goal here is to maximize filtration rate. One should be able to see that the experiment is in standard order. Now, of course, one would hope that the experimenter ran this experiment in random order. The observations are also in the column labeled filtration rate. The design is essentially a 4-dimensional hypercube. We can't portray this exactly, so what we will do is set up 2 cubes based on the levels of factor D. The responses have been placed at each of their corresponding corners on the cubes. The table shows the estimates of the effects. Based on the size of the effects, it would seem that the ones in bold are most likely the real effects. Notice that there is not an estimate of S. Again, this is because we only have one replicate at each corner of the design. You will see shortly that all of this is based on degrees of freedom. Degrees of freedom are a geometrical concept that you will learn more about in regression. In this class, we will use a loose interpretation of DEF. Degrees of freedom are the amount of information we have available from the sample or observations. Each observation contributes 1 degree of freedom. So in our case, we have n degrees of freedom to work with. A degree of freedom is used up each time that we estimate a parameter. Since we always estimate the overall mean, we will keep 1 df for that. So essentially we have n1 free degrees of freedom. The degrees of freedom needed to estimate an effect is always the number of levels minus 1. So for the 2 to the power of k designs, we will need 1 df for each main effect. This is also true for interactions. The reason is that we take the df from each main effect that makes up the interaction and multiply them together to get the df for the interaction. So in this case, all main effects has 1 df. So any interaction effect will also have 1 df. This holds for any higher order interaction also. You should be able to convince yourself of this. This means for our filtration example, since we have 16 runs total, we have 15 df to work with. The number of effects for the 2 to the power of k design is 2 to the power of k-1, which in this case is 15. This means that if we want to estimate all of the effects, we have to use up all of the available df, which should lead you to see that there are no df available to estimate error. Now what? The sparsity of effects principle implies that most systems are dominated by low order terms. In our case, that means main effects in two-way interactions. This is not an indication that we can only study main effects in two-way interactions, because there may be some instances where a higher order interaction is real. So we need a tool to indicate which of these terms are most likely real. To do this, we will use probability plots. Daniel came up with the idea of using a normal probability plot in 1959 to identify active effects for two-level designs. This is a plot of the effects versus the percentages from a normal distribution with a mean 0 and some constant variance. Because of the CLT, it is reasonable to suppose that the distribution associated with the effects in normal. This is where the equal variance property for the effects in a 2 to the power of k is so critical. If the effects are truly zero, then these effects will fall on a straight line. This works again because of the +1/-1 coding. Putting this all together means that if no effects are active, then the effects look like an independent and identically distributed sample from a normal distribution. So, in this case, the points should look well behaved if plotted on a normal probability plot. The effects that occur far away from the line are deemed real. Realize that these plots are subjective. The effects that are on the line are most likely not real and can be used to get an estimate of error. Here is the normal probability plot for the filter example. Based on the plot, it seems that main effects A, C, D and interactions AC and CD are real. An alternative to the normal probability plot is the half-normal plot. It is similar, except here we take the absolute value of all of the effects before they are plotted. Some analysts believe that this plot is easier to interpret. Most of the time, both plots will yield the same results. If it seems like the effect may not be on the line, do not assume that it is not active. Based on this plot, we get the same results as we did using the normal probability plot. Notice that none of the active effects involve factor B. We will use this to our advantage by projecting the design, so the points that are off of the line are active. From here we would finish the analysis as we did in the previous lecture. Even though some packages create the test for LOF, since the reduction of terms does not create replicates, we cannot consider this a pure error situation. Therefore, you should not run the test for LOF. Here is an example which has 4 factors and 1 response. This is an unreplicated design. Again, you should get in the habit of denoting qualitative and quantitative factors. This is a printout of the experimental setup with response. Notice the table on the right that identifies each factor in their natural variables. Based on the normal probability plot, we see that the main effects A, B, and D seem active, and the interaction BD also. This output yields the results for the hypothesis tests on the effects and allows us to decide on which effects should be kept in the model. Notice here that we have maintained hierarchy since both main effects B and D are in the model. In this case, you would have hidden replication. You should be able to convince yourself of this. Recall that this is not true replication, so we do not have any information on pure error. A regression model would then be used with the remaining factors to determine what the estimated response would be throughout the experimental region. Once we get the model, we still need to check to see if model assumptions hold. We assume that the errors are independent, have constant variance, and follow a normal distribution with mean 0. We can check these assumptions using the residuals. Residuals are the difference between the actual observed values and the values that are given by the model, or the mean value for a given set of SUBI. We check the assumptions using residual plots. We would like the residual plots to show no patterns. Beware of trying to find patterns on plots with a small number of points. I would not make any judgment on plot with less than 16 points, and that is pushing it. Each of the plots can be used to check a specific assumption. Here are the residual plots for the conversion example. Let's first examine the plot versus order, assuming that the runs were randomized. It seems to show a random ordering. Now that there doesn't seem to be any issues. To check for equal variance, we will look at the plot of the residuals versus the fits and each factor. It seems from this plot that there is not a pattern. The next three plots are residuals versus factors A, B, and D. You should remind yourself that we can't tell what is going on in between the factor levels. If the factor is qualitative, there is no in between values. Based on this plot versus factor A, it seems that there is not a pattern. There doesn't seem to be an issue with factor B. There also does not seem to be a variance issue with factor D. So we can conclude that there does not seem to be a homogeneity of variance issue. This is a normal probability plot of the residuals. The hypothesis that is being tested is that the distribution of the residuals is normal. Based on the p-value, we would fail to reject the hypothesis that the standardized residuals come from a normal distribution. In this case, the model seems to be adequate. Sometimes, people like to use prediction intervals as a means of assessing the predictive ability of their model. They will run their experiment and create a model. They use the model along with new observations measured at x coordinates inside the experimental region to see how well the model predicts the values of these new observations. This is a good technique as long as you have the resources to utilize it. Here is an example of this with the conversion example. Here are a set of x variables and new response values to test using prediction intervals. Based on the fact that all of the new observations fall inside of the prediction intervals for their corresponding x's, we would conclude that this model did an adequate job predicting future responses. Contour plots are plots of the surface. They are called contour plots because we create contours that represent a fitted response. When the model is first order, these contours are straight lines. These lines will bend if we add the interactions, and will be ellipses for second order models. For this example, we can see that the model is linear without interaction. This is because the contours are straight lines. We can read the fitted response for any combination of catalyst amount and reactant concentration. We have three important factors for our conversion example, A, B, and D. How do we create a contour plot for this situation? We know that contour plots are created using two factors. Well, we need to create the plot using two of the factors, while holding the third constant. In this particular case, let's assume that our goal is to maximize conversion. We will hold the factor constant and create the plot using B and D. This is because there is an active interaction between B and D. The question now is, how do we know at what level to hold A? We should use our main effect plot and set the level of A at the position that maximizes the average response. You should also realize that when only main, linear, effects are active, the experimenter usually has more faith in the contour plot. The existence of a 2-phi linear x linear implies some second order behavior, so terms such as b squared and d squared might be active as well, even though we can't estimate them. However, predictors at the corners of the design are still unbiased. Based on our main effect plot for A, the average response is maximized at the low level. Here is the contour plot using factors B and D. Notice that the contours are no longer straight lines. This is an indication that there is an interaction in the model. In order to maximize the average response, we should set B to its high level and D to its low level. Notice that if you are trying to get the max or min responses, that the solutions will also be a corner, and, from the interaction plot of B and D and the main effect plot of A, you can figure this out directly. This works out when the model is first order or first order plus interaction. Notice that up to this point we have not talked about any other models besides first order or first order plus interactions. This is because for the designs we have looked at, we have not had enough levels to even fit any other higher order model. Some experimenters employ center points to decide between a first and second order model. Also, the addition of center points allows for replication of some points in the design. A center point is a run by which the levels of each factor are set to the midpoint. If we code the factor levels so the low setting is denoted by -1 and the high level is denoted by +1, then we can represent the level for a center point with 0. This, of course, only works for quantitative factors. We usually employ somewhere between 3 and 6 center points. You will see why this is later in the course. Since the center point is represented by zeros, it does not affect the calculations of the diagonals of the XX matrix that represent the effects. Therefore, it does not affect the variance of an effect. A center point is not considered an addition of another factor level because we are not including it in combination with any other levels of any of the factors. We consider it one unique run. The main use for center points is to test for curvature. If we find significant curvature, then we may want to add more runs to try to model the curvature with a second order model. If the mean for the factorial points minus the mean for the center points is small, then we can conclude that the surface is better represented by a plane. We can check this using a hypothesis test. The null hypothesis is that the sum of the quadratic terms is 0 and the alternative is that it is not equal to 0. It'd be better if we could test if each quadratic term was 0, but we don't have enough information to do this. Therefore, if the true surface is represented well by a second order model, then the difference in the mean for the factorial points and the mean for the center points is an unbiased estimate of the sum of the quadratic effects. We can use this quantity to calculate the SS for the pure quadratic terms, and then create an F-test using the MS for pure error based on the center points. For this F-test, the numerator df would be 1. The reason for this is we only have one unique run, the rest is replication. So we get 1 df for the pure quadratics, and NC1 df for pure error. Here is just a general method that could be used to analyze these types of experiments. 1. Use the center points to create the test for curvature. 2. If you find significant curvature, this simply gives you information that you can't reliably predict the response at the center of the design, and so the contour plots in the interior should be regarded with suspicion. You may wish to stop the analysis since a higher order model seems to be a better fit. From here you would need to add more levels to each factor so that you have the ability to fit a higher order model to the data. 3. If you do not find significant curvature, then continue with the analysis as we have been doing. Since center points are replication, they can use to estimate error. This should only be done in addition to other replication in the design. Usually we only run a small number of center points, which means that we would be estimating variation with a small number of observations. Also, center points are usually set up to be where the process is typically run. This means that the process probably runs well there, and the measure of variation will probably not be representative of the entire region. If you have a small number of runs left and would like to use them for replication, you are probably better off running them more extreme locations, such as the corners of the experimental region. Now suppose that we added 4 center points to our conversion example. Let's use this information to analyze the experiment. We can create the test for curvature using the MS for the pure quadratics and pure error, which are given in this table. Based on the large p-value, it seems that a higher order model isn't necessary. We can conclude from this that since there is no significant curvature, the conclusions that we came to initially are valid. One issue with center points is that they can only be used for quantitative factors. This is because for a qualitative factor, it doesn't make sense to consider a level in between the high and low. For example, if we had a factor called machine, and we had machine A for the low level and machine B for the high level, we could not get an in-between level for the two machines. Also, remember that for a qualitative factor, the level names are arbitrary. This means that I could have just as easily called those machines 1 and 2, or machines 100 and 200. If we have a situation where we have a mix of qualitative and quantitative factors, and we want to utilize center points, then we need to have the same number of center points for each level of the qualitative factor. For example, let's assume that we have the three-factor experiment above, where catalyst type is qualitative. Now we want to run 4 center points in the design. The center point would consist of the temperature and time at their middle levels, and catalyst type at either the high or low level. Then another center point would need to be run at the other level of the catalyst type. Notice on the cube that we have a center point on both faces for the catalyst type factor. So if we wanted 4 center points, we would actually need to run 8 overall, 4 at the low level of catalyst type and 4 at the high level. It gets even more complicated if we have multiple qualitative factors. Next time we will talk about fractional factorials.